Hello all. So this is the second session of organic symmetry classes. In this session we will be focusing on a different class of reactions of haloalkanes. Haloalkanes, their substitution, elimination, competition. Okay, so nucleophilic substitution and elimination reactions, it is very common for haloalkanes, and let's see their comparison. So today's topic is nucleophilic substitution versus elimination of haloalkanes. At times it is a bit confusing section also. We have to think about a lot of factors while dealing with this section, and every time there is a competition between SN and E reactions for haloalkanes. That is the complexity of this section. Here, first of all, if we generally think about the nature of nucleophilic substitution and elimination reaction, the one prerequisite is that there should be a leaving group present in the substrate. And if leaving group is present, then there can be nucleophilic substitution or elimination reactions possibilities. And we know that halogens are very good leaving groups since halides are very stable, right? They are less basic, they are less reactive, they are stable also. Halides are stable, therefore halogens are good leaving groups. That makes the nucleophilic substitution and elimination reactions very feasible on haloalkanes. These are the interesting or favorite reactions of haloalkane substrates. Okay. Now, if we think about the mechanism of these two reactions, there is a duality in both cases. Mainly, two types of mechanisms are present for nucleophilic substitution, and two types of mechanisms are mainly present for elimination reaction as well. So, we will first look into the details of the very fine details of the nucleophilic substitution elimination mechanisms, and then only we will be going to problems related to this topic. While talking about nucleophilic substitution, let's call it SN in short. Nucleophilic substitution could be either SN2 mechanism or SN1 mechanism. SN2 mechanism is the natural mechanism which is driven only by steric factors, natural factors. If steric factors are low, if steric hindrance is low, then SN2 is very feasible. If sterics is very high, then it is not possible. So it is mainly driven by only one factor, that is steric factor. And SN1, it is a special mechanism. SN1, I will call it a special mechanism because there is a carbocation formation. Carbocation, it's very less stable species. So such a species has to form in SN1 mechanism. So it is a special mechanism as it involves carbocation intermediate. And SN1 mechanism happens only if more than one criteria match. First of all, let's outline the two mechanisms. We have our haloalkane Rx, let's call Rx, and we are taking a nucleophile, let's say NO minus, and SN2 means just it is doing a backside attack and the halogen leaves as a halide ion. Single step reaction, right? Single step reaction RNU, or more correctly we can represent it like this: NUR because it is approaching from the opposite side as that of our halogen, the leaving group, right? And X leaves. So X is a good leaving group. It is manifested in this reaction. And if we look at the SN1 reaction, SN1 mechanism, then there is multiple steps. First of all, X has to leave, right? First of all, X has to leave. Then only nucleophile enters. And it forms R plus, which is not very stable. These are reactive intermediates, right? So such a special species has to form in this reaction. Carbocation intermediate. And after that, the nucleophile attacks. So there is a temporal difference. There is a timing difference for the two steps. First, halogen leaves. Then after that, after a few milliseconds, nucleophile attacks. We get products. It could be RNU or NUR. Or means mixture of both products can form because carbocation is achiral. It is planar. Okay, so that is the mechanism. And SN1, when it is favored, SN1 is favored only if more than two criteria or more than at least two criteria match. SN1 occurs only if two or more of the following and the criteria are, first of all, stability of carbocation. Carbocation is a product of this mechanism, meaning it is an intermediate of this mechanism. It is a product of first system. It has to be stable. Then only step 1 happens. Then only SN1 can occur. So stability of R plus is the prime factor. Stability of carbocation its principles we know from basics. And secondly, use of polar protic solvent. Polar protic solvent, since there is a hydrogen bonding possibility, polar protic solvent molecule with a delta plus containing hydrogen, and there is a hydrogen bonding possibility which highly solvates the anion, the leaving group anion, thereby promoting the dissociation of Rx, right? Thereby promoting the dissociation of Rx. So polar protic solvent is stabilizing this species in the medium, thereby promoting carbocation formation. So that is a second criteria in order to SN1 reaction to occur, SN1 mechanism to happen. And another criteria would be steric hindrance to SN2. So some cases SN2 is difficult, SN2 will be difficult. In such cases it is an alternative pathway. SN1 is an alternative pathway. So steric hindrance to SN2 is another criteria which may promote SN1 mechanism. And finally, weak nucleophiles. For example, OH minus is a strong nucleophile, H2O is a weak nucleophile. Similarly, OR minus alkoxide ions are strong nucleophile, and the protonated form ROH, it's a weak nucleophile. Weak nucleophile generally promotes SN1 mechanism, and none of them exclusively promotes SN1 mechanism, more than 2 or 2 of these criteria has to match, then only SN1 reaction occur. Otherwise, simply if we use, let's say if simply we use polar protic medium, let's say we are taking N-propyl bromide in H2O, the reaction will not be SN1 because carbocation is not very stable. This is a special mechanism. So more than one criteria, at least 2 criteria should match. At least 2 criteria should match. So we will be every time evaluating the given conditions and decide whether SN1 or SN2 is happening over there. And these are the general aspects of SN1, SN2 mechanisms and the general aspects of nucleophilic substitution reaction. And remember that nucleophilic substitution is the generally preferred reaction of haloalkanes, and the second one is elimination reaction. And within nucleophilic substitution, SN2 is the more preferred mechanism in general, natural mechanism, because it is just controlled by steric effects. Already halogens are good leaving groups. So if there is a nucleophile, then it can directly displace the very good leaving group and do a nucleophilic substitution, right? So SN2 is a natural mechanism. So have a flavor of that. Now let's see what is the duality of mechanism in elimination reactions. In elimination reactions. Let's simply call E. In E reactions, we know there is E2 and E1 mechanism mainly, right? E2 and E1 mechanism mainly, and E1CB rarely, as you see in aldol condensation reaction, there is an E1CB. But generally we will be talking about E2, E1 reactions. And E2 is the natural mechanism. Strong bases do E2 reaction. Strong bases do E2 reaction. By strong bases we mean OH minus or alkoxide ions or amide NH2 minus. These are the general strong bases, and E2 is therefore the natural mechanism. It occurs in single step, you know. Okay, sterics is not a factor controlling E2 in general. Steric have minor impact only on E2 reaction, or in general elimination reaction there is a minor impact only for steric factors, which we will see. E1 mechanism is a special mechanism. And weak bases do E1 mechanism. Special mechanism because there is a involvement of carbocation intermediate. Yes. Now let's quickly outline the mechanism of both pathways. E2 reaction. Here we cannot simply write Rx because you know it is a beta elimination. Nucleophilic substitution, you know, it is just happening on the carbon to which leaving group is attached. But elimination reaction, you know, it is a way to prepare pi bond. Therefore, we need to consider 2 carbons, at least 2 carbons, while dealing with this type of a reaction. So let's consider alpha and beta carbons. Yes. If it is E2 reaction, then we are taking a base. We are taking a base, let's call B minus. B minus just takes this H plus, and that bond electrons shift to here, and thus halogen leaves. Remember here also, like in SN1, like in SN2, in elimination also, the role of halogen is just to leave. It is a good leaving group. Okay, that is why elimination SN reactions, the prerequisite is there should be a leaving group present in the substrate. Okay, so this happens, base takes acidic hydrogen and thereby halogen leaves, and the products will be C double bond C plus base becomes conjugate acid of base, and then halogen leaves us halide ion. that happens in one shot. And this was the natural mechanism. And if it occurs by E1, if the elimination occurs by E1, then X leaves first, like in SN1. So the first step is similar to SN1. First step is similar to SN1. Halogen leaves and we get carbocation intermediate. Thus, this is also promoted by polar protic solvent, and C plus forms. C plus forms, and later base comes. This time it's a weak base, therefore I am not applying the negative charge. Just B will be sufficient here because it's weak base, and base takes H plus and produces the pi bond plus BH plus. Base forms the conjugate acid. Okay, so things happen in at least two steps, and you know that in SN1 E1 reactions carbocation formation is there, therefore rearrangements are possible. May rearrange definitely if there is a possibility. Similarly in SN1 also, you know, rearrangements are characteristics of SN1 E1 mechanisms due to carbocations, and the carbocation involvement is the speciality of both these mechanisms. And here you can see that in elimination reactions, base takes a peripheral hydrogen, right? Base abstracts or takes a peripheral hydrogen from the substrate, from the haloalkane, let's say. Therefore, steric hence the effect of steric factors are low in elimination reactions. In elimination reactions, you may remember that tertiary haloalkane will be more reactive in E2 and tertiary is more reactive in E1 also. This is based on carbocation stability, that is based on the alkene stability. Okay, so anyway, at the end of the day, both mechanisms are highly favored by tertiary haloalkane. And remember, E2 is the preferred mechanism of elimination, and E1 occurs if the base is weak. E1 occurs if the base is weak. And also, you know, there should be polar protic medium also to support this cleavage of CX bond. Yes, that is secondary. Now, regarding the nature of products in both cases, generally sets of rule predominates, or sets of products predominates in E1 and E2 reactions, in elimination reactions in general. Generally, the more stable alkene is the major product. That is the meaning of this statement. Sets of product means more stable alkene predominates. That is a major product in general elimination reactions. But Hofmann product may predominate. The less substituted product, alkene, predominates if under the following conditions. Hofmann product predominates under the following conditions. First of all, use of bulky bases. Use of bulky bases. Let's think about alkoxides in general. Alkoxides are very strong bases. All alkoxides are strong bases. Therefore, E2 is the preferred mechanism. E2 is the general mechanism of alkoxide haloalkane interaction. And among alkoxide, if we take methoxide, ethoxide, etc., they will be giving sets of products. They are small alkoxides. And if we take tertiary butoxide or tertiary pentoxide, they are bulky bases. They are bulky bases. Therefore, steric factors operate. So, perhaps this is the only case in which steric factors are present in the elimination reactions. Okay, here steric factors operate. In almost all other cases, there is no steric impact to elimination reactions. Steric factors operate, therefore, Hofmann product is major in such cases. Okay, with small alkoxides, we get sets of product, normal product, and like in every case. And with bulky bases, that is the first case where we get a Hofmann elimination. With bulky bases, we get Hofmann product as the major one. That is one case. And secondly, Hofmann products. We are talking about Hofmann predominance. Hofmann product predominates under the following condition. One is this, or second is when leaving group is fluorine or trialkyl ammonium. When leaving group is fluorine or trialkyl ammonium, then also Hofmann product is observed as the major product. These are the few cases, bulky base using cases, and these leaving groups present cases in the substrate. These are the few cases where we see Hofmann product dominating in the product mixture. Okay. Otherwise, in any E2 or E1 reactions, we will be seeing more stable alkene as the major product. Yes. In this session, we will be focusing on certain nucleophiles or bases. So, target reactions of this session will be haloalkane, their reaction with OH minus or alkoxides or H2O or alcohols. Okay, these are the commonly observed nucleophiles or bases, and in their cases there is a lot of confusions generally happening in this topic. So, haloalkane, if treated with hydroxide, alkoxide or H2O directly or alcohol directly, what is going to happen? Is it going to give us nucleophilic substitution or elimination? So, remember that in every case, in the case of haloalkanes, there is a competition between SN E reactions, and haloalkanes in general, SN is the more favored reactions, and whenever SN is difficult, generally speaking, whenever SN is difficult, then elimination occurs. Okay, then elimination dominates. That is the only correct statement. So, haloalkanes generally like to undergo nucleophilic substitution. So, let's take these few nucleophiles and analyze their cases. Okay, OH minus alkoxides. Alkoxides you have methoxide, ethoxide, propoxide, tertiary butoxide, etc. H2O. Alcohol, we can talk about methanol, ethanol, tertiary butyl alcohol, etc. And such cases, what is going to happen? Whether it is SN1, SN2, E1 or E2 dominating in these cases, that is our question. Most of the cases you see, what is a major product? We will be given a haloalkane and we will be given one of these nucleophile or bases, and they will be asking what is a major product and what would be the mechanism. Okay, such questions are very common if you analyze the previous questions of past 11 years. Yes, now haloalkanes, the reaction with these selected reagents. Let's summarize a few general points. Let's list down some general rules regarding these reactions. First of all, reaction of haloalkanes. Haloalkane, let's denote Rx. Reaction of Rx with small solvent molecules is generally nucleophilic substitution. Okay, whenever you see a haloalkane H2O, a haloalkane alcohol like methanol, or haloalkane ethanol, above the arrow mark ethanol. In these cases, we should be imagining about nucleophilic substitution, which is the more favored reaction of haloalkane. And by small solvent molecules, I mean H2O, CH3OH, methanol, and C2H5OH. Of course, small solvent molecules, nucleophilic solvent molecules, that is by definition it is present, nucleophilic solvent molecules. For clarity, let me write that also. Nucleophilic solvent molecules. If it is CCl4, no reaction. If it is CHCl3, no reaction with haloalkane. If we take nucleophilic solvent molecules, in that case, there is a general possibility of nucleophilic substitution on the haloalkane. And you may remember that Rx, H2O, we get alcohol, right? Rx, methanol or ethanol, CH3OH or C2H5OH, we get ethers. These are the product. And these reactions, such reactions are generally called solvolysis reactions. Solvolysis reactions. So in solvolysis, using these solvents, we will be getting SN as the mechanism, as the type of reaction. And here we can do few more generalization that if you take tertiary haloalkane, then the mechanism, we know SN could be SN1 or SN2. If you take tertiary haloalkane, it is like only SN1 reaction. If you take secondary haloalkane, there will be mainly SN1 reaction. And if you take primary haloalkane, it is more like only SN2 reaction because of the very less stability of carbocation. You can see that these are polar protic solvents, right? H2O, methanol, ethanol, these are polar protic solvents in which SN1 can occur. SN1 can occur if more criteria is present, right? We already have polar protic solvent, then if carbocation is also stable, then it will occur. Otherwise, it will not occur. Primary haloalkane, put in water, if reaction happens, that would be by SN2 mechanism, no rearrangement, right? That is why I said SN1 reactions are special mechanisms. They are special reactions that occur by looking at more than one criteria. At least two criteria should be matching for that mechanism to occur. Otherwise, SN2 will occur. SN2 is a natural mechanism that will happen. Yes, primary haloalkane only SN2, and primary haloalkane with hindered beta carbon, with sterically hindered beta carbon, in that case SN1 reaction can occur. Okay, whenever there is a steric hindrance for SN2 attack, then also SN1 can occur. That was one of the points we had listed in the factors governing SN1 reaction, right? Stability of R plus, that is why tertiary show this reaction, and use of polar protic solvent, of course, and steric hindrance to SN2, right? Steric hindrance to SN2 if present, then SN2 cannot occur, because SN2 occurs only if the nucleophile is directly able to attack on the R, right? If there are bulky groups, then it cannot directly hit on the R. This SN1 will be the alternative mechanism. Weak nucleophiles, that is another case, weak nucleophiles. Okay, these are the few instances. Let's take one example here. Neopentyl CH3, CCH3, CH3, CH2, Br. Neopentyl bromide. Let's say we are treating with ethanol. Okay. If we are doing this reaction, we can see that this is alpha carbon, this is beta carbon. Beta carbon is too much crowded. So SN2 reaction is highly hindered here, and this happens through SN1 mechanism, therefore. Okay, this happens through SN1 mechanism, therefore. And SN1 mechanism, first of all, there is a carbocation formation, CH3, C, CH3, CH3, CH2 plus with the loss of bromide. And if carbocation forms, you know, there will be rearrangement. SN1 mechanism, their characteristic rearrangement is their characteristic. CH3, C plus, CH2, CH3, CH3. Such a cation forms, and later our ethanol, that is a nucleophilic solvent, ethanol attacks, and then H plus is lost, giving us the main product. Okay, so that will be this ether. This is an ether, right? If alcohols do solvolysis, we will get ether. If H2O do solvolysis, we will be getting alcohols. So that is an illustration for beta crowded primary haloalkane doing SN1 reactions, because SN2 is very difficult. SN2 is very difficult here. Okay, whenever SN2 is difficult, then also this is difficult. Whenever SN2 is difficult, then also SN1 may occur if there is multiple conditions matching. Here polar protic solvent was present. Okay, so that is the first rule. The reaction of haloalkane with small solvent molecules generally follows nucleophilic substitution mechanism. They are solvolysis reactions, and mechanism we can decide by looking at the nature of substrate and conditions. Second rule is that haloalkane, if we treat with aqueous OH minus, it will be nucleophilic substitution. And haloalkane, if we treat with alcoholic OH minus or less polar solvent, alcohols are less polar solvents, then it will be mainly elimination reactions. Okay, so haloalkane OH minus in aqueous medium shows nucleophilic substitution reaction, and haloalkanes OH minus in alcohol or less polar solvent like acetone medium, it shows elimination reactions. And one other case is tertiary haloalkane. If we treat with alkoxide, any alkoxide, we get elimination reactions. Well, it could be methoxide, it could be ethoxide, it could be tertiary butoxide, any alkoxide. If you treat with tertiary haloalkane, then elimination is the main reaction. Sometimes we say there is no substitution also, because what would be the reason? You can imagine about the reason for this. OR minus are strong bases also. We know these are good nucleophiles, and these do primary haloalkane and secondary haloalkane, mainly nucleophilic substitution reactions. And tertiary haloalkane, nucleophilic substitution reaction is difficult. Nucleophilic substitution means these are strong nucleophiles, therefore we are talking about SN2 reactions, not about SN1. First of all, we should be thinking about SN2, that is a natural mechanism. Okay, so SN2 reaction will be difficult on tertiary haloalkane due to steric factor, right? SN2 is driven by steric effects, controlled by steric effects. And therefore, when alkoxide thinks, oh, it is also a strong base, right? It is a good nucleophile and strong base also. And we know that haloalkane like to undergo elimination reactions also. Okay, so if it is a good nucleophile, it can undergo nucleophilic substitution. If it is a good base also, then it can show elimination reaction also, right? It has an alternative reaction. So that happens here. Okay, in this case, this acts as a base. Okay, its base character will predominate and we get alkene product. We get elimination products. Yes. So if we see any haloalkane, tertiary haloalkane with an alkoxide base, it could be any alkoxide, all are strong bases, and they show elimination reactions. Yes. So aqueous OH minus alkyl halide, nucleophilic substitution, alcoholic or less polar solvent OH minus haloalkane show elimination reaction. Tertiary haloalkane with alkoxides show elimination reaction because OR minus is a base also. That is the reason here. Okay, because OR minus is a base also. Right. So that is the second rule. And now we have a third rule, like increase in steric factors promotes elimination reaction. Increase in steric factors promotes elimination reactions. Promotes elimination reactions over. We are talking about the competition between topic is nucleophilic substitution versus elimination, because both are favorite reaction, although nucleophilic substitution is little more favorite than elimination reactions. Okay, so haloalkane like to undergo mainly SN reactions and later elimination reaction. So mainly SN reaction happen, and if we are little more careful, then elimination reactions can be made as the primary reactions of haloalkane. We are talking about that cases. Okay, if we are taking H2O or small alcohol molecules, such small nucleophilic solvents, then we get SN reactions. If we are taking these conditions, then we will be getting corresponding reactions. And if we are increasing the steric factors, then we may get more of elimination products. Okay, then we may get more of alkenes in the product mixture rather than the alcohol or ether products. Yes, increase in steric factors promotes elimination reactions. Let's see how it is impacting here. First case, we can see primary. If we move from primary to secondary to tertiary RX, there is an increase in elimination, the fraction of elimination reactions. So the idea is sterics at alpha carbon increases, right? Primary to secondary to tertiary means alpha carbon is becoming more and more crowded. If alpha carbon is becoming more and more crowded, direct nucleophilic attack will be difficult, right? Therefore, an alternative is elimination reaction. Thus, we can give preference to elimination reactions. So, if we increase sterics at alpha carbon, the preference for elimination increases. Then, if we take tertiary butyl alcohol instead of an ethyl alcohol or methyl alcohol, or tertiary butoxide instead of ethoxide, in both these cases, elimination gets more preference. That is, steric at base component increases, right? Bulkiness of nucleophile or base increases, then also preference for elimination increases. So, steric factors means it could be anywhere. It could be on the reacting center alpha carbon. It could be on the base component also. As the base become bulkier and bulkier, it cannot directly attack on the alpha carbon, right? The nucleophilic substitution occurs if the nucleophile is able to attack on alpha carbon, right? Alpha carbon is the leaving group attached carbon, and alpha carbon we have multiple groups present, and by skipping all of them, the nucleophile has to attack on the alpha carbon, right? That is difficult if bulkiness is high. Yes, so if alpha carbon gets more crowded, similarly if the base gets more bulky, in both cases elimination preference is increasing, chances of elimination is increasing, or in other words, the chances of nucleophilic substitution keep on decreasing on the alkyl halide substrate. As an illustration for this criteria, let's take an example quickly. Let's take isopropyl bromide. Isopropyl bromide, if we treat with ethoxide C2H5O-, if we treat with C2H5O-, we get nucleophilic substitution product. We get nucleophilic substitution product. On the other hand, if we treat this same compound with tertiary butoxide, on the other hand, if we treat the same compound with tertiary butoxide, tertiary butoxide is bulky, and you know that this is secondary haloalkene. Secondary haloalkene, it is not primary. Okay, if we move from primary to secondary, then also elimination preference increases, and if we increase the bulkiness of base, then also, or nucleophile, then also preference for elimination increases. So, two criteria are matching for elimination reaction, right? There is an increased sterics at alpha carbon by rule 1. By this rule, we are increasing the preference for elimination, and if we are using a bulky base or bulky nucleophile as well, then we can say that elimination becomes the predominant reaction, and tertiary butoxide, secondary haloalkene, we get this product by elimination reaction. Okay, that is a steric impact on elimination reaction. As sterics increases, preference for elimination increases. So what happened here? Tertiary butoxide could not attack on this carbon. Tertiary butoxide could not attack on this carbon. Instead, it had an alternative, because haloalkene may undergo nucleophilic substitution, and if nucleophilic substitution is difficult like this, then another alternative is there, elimination reaction. In both way, halogens can leave, right? In both way, halogens can leave and they are happy. So, tertiary butoxide, then it shows elimination reaction due to steric factors. Ethoxide, it shows nucleophilic substitution due to low sterics, right? So, remember, this is the favorite reaction. More favored reaction is SN, and we make elimination preferred and preferred by modulating the conditions using the above principles. Yes, so increase in steric factors promote elimination reactions. Yes, so these are the first two points under the third rule, and then increase in sterics can be occurring at beta carbon as well, like this. Let's say this is a haloalkene, and if we made it like this, now we can see beta carbon is more crowded. Beta carbon is more crowded. Thus, this type of a change also promotes elimination. Sterics increasing it. Increase in sterics at beta carbon increases, preference for elimination increases. So in case of secondary haloalkenes, this is secondary haloalkene which already has a like more favorance of elimination reaction if we compare with primary, and but there is an equal competition with nucleophilic substitution we saw in the previous example. Secondary haloalkene, there can be equal competition between, at times it is like 50-50, there can be equal competition between the elimination and nucleophilic substitution reaction because it is a borderline, right? If you take tertiary, only elimination reaction. If you take primary, then mainly SN2 reaction. And in this case, right, in secondary case, there is a confusion. Slight variations of the reaction conditions will make one of them dominant. Okay. So in that background, we are saying that if you take a secondary haloalkene, if we increase the crowding at beta carbon, then the preference for elimination increases. Preference for elimination increases. So generally, you can remember that increase in steric factors promote elimination reaction because in SN reaction there has to be a direct attack of nucleophile on the middle carbon, but in elimination reaction there is no steric control. There is a peripheral hydrogen abstraction only happening by the approaching base, right? That is easy. So whenever steric is high, elimination reaction may occur therefore. Okay? Yes. Now, as a final rule, heating favors elimination. High temperature is another factor which favors elimination. It favors means it gives a little more preference for elimination, that's it. Otherwise, if there is a heating, there should be elimination. It is not like that. If we want to increase the percentage of elimination product, that is a reality. There is a competition between SN and elimination reaction always. We cannot have perfect elimination or perfect substitution every time. Most of the cases, there is a mixture of products. So in that case, who is more than 50%? That is our question. Okay, who is the major reaction? So if we promote, if we want to promote elimination reaction, this is one criteria. Do more heating. More heating favors or may give more preference to elimination. Yes. So these are the 4 simple rules which we should be working on while deciding whether a reaction of haloalkene is SN or elimination. Okay. So once again, the reaction of a haloalkane with small nucleophilic solvent molecules like H2O, methanol or ethanol is solvolysis. That is generally SN reactions. We get alcohol or ether products. And if we take aqueous OH minus, we get nucleophilic substitution alcohol products. And if we take alcoholic OH minus or OH minus in less polar solvents, then we may get alkenes as the major product by elimination reaction preference. And if we take an alkoxide, any alkoxide, and try to react it with a tertiary haloalkene, then we get elimination as the main reaction, and we get alkene as the main product. Elimination gives alkenes. And then if we increase the steric factors at alpha carbon or at the nucleophile center or at the beta carbon, then also preference for elimination keep on increasing. And finally heating, if we give heating, then there is a more chance of elimination reaction. Yes, that way we can raise the preference for elimination over nucleophilic substitution. Remember again, nucleophilic substitution is the main reaction. It is a more favorite reaction of haloalkene. So in order to make elimination preferable, we have to focus on, we have to work on multiple factors like this. Yes. Now let's see few problems related to this topic. These are all again from previous questions. Let's try to solve them. So we have made every tools ready. We will be using those tools to predict the products of these reactions. The major product Y in the following reaction is, we can see a secondary haloalkane, and we can see ethoxide, which is a strong nucleophile, strong base, and we can see that beta carbon is crowded also, right? We can see that beta carbon is crowded also, it is having a methyl group also. Therefore, we are kind of clear that this is going to give us an elimination reaction. First reaction is going to be an elimination. Also, to promote this factor, they have shown heat also, right? So, all the factors are favoring. There is enough steric factors which promote elimination reaction. There is a strong base present also which promotes elimination reaction. There is heating also which promotes elimination reaction, and thus we can say that this is going to be elimination reaction. And if it is elimination reaction, it could be by E2 mechanism, because this is a strong base. ETO minus is a strong base. So E2 elimination occurs first. E2 elimination occurs. We know sites of product is the major product. Yes. So if we take ETO minus ethoxide, ethoxide takes this beta hydrogen, not this beta hydrogen. If tertiary butoxide was taken, then we may get alkene over here, Hofmann product. But this is normal base, right? Small base, strong base also. Thus we get elimination sites of product formation also. This would be the product. And that is our X. So first of all, our confusion must be like this. By looking at this reaction, whether it is a nucleophilic substitution or elimination reaction, this should be our confusion in our mind. And then we have to decide. We know that generally SN2 reaction is or nucleophilic substitution is the preferred reaction, but we know that there is another possibility also, elimination, which is preferred by multiple factors including steric factors, and those factors are favoring elimination. In this case, this is a secondary halide. Primary to secondary to tertiary elimination preference increases. So it is a borderline case, and we are using sterically hindered. We have steric hindrance at beta carbon also, so that further promotes elimination reaction. And we have taken a strong base also, which again promotes elimination reactions, and heating is also present, which favors elimination reactions. Thus we can decide that this conversion is going to be elimination in preference. It would not be a nucleophilic substitution. And then we have to decide to predict the major product. Later we have to decide which is the mechanism, E1 or E2. Then we can see that easily it is an E2 reaction, because it is a strong base. Strong bases do E2 reaction, only weak bases can do E1 reactions. Yes. That is the principles behind this conversion. And now then they are doing an addition reaction which we covered in the last session, HBr. First of all, the carbocation forms. First H plus adds. We get a more stable carbocation like this, and then Br minus. Then Br minus attacks, and we get such a tertiary haloalkane product. Yes, that product is this one. This is looking little merged with option 1. Let me redraw the option. Option 3 is actually this. Okay. Now, this is second question. The major product in the following reaction is haloalkanes reaction. It is whenever we see a haloalkane, we should be first thinking about the substitution reaction, then only for elimination. So first of all, we know that this is secondary haloalkane. And we are using tertiary butyl alcohol. Tertiary butyl alcohol. If it was a H2O, if it was a methanol or ethanol molecule, then there is no doubt that it will do a SN1 reaction, right? SN1 reaction, our rule 1. Okay, the reaction of haloalkenes with small nucleophilic solvent molecules show SN reactions, and this is a large solvent molecule. Tertiary butyl alcohol is a solvent also, it is a liquid, and it is a large solvent molecule, right? Therefore we cannot have a direct SN reaction. Steric factors are there. Remember our rule, increase in steric factors promote elimination reaction. We have written, if we take tertiary butyl alcohol, this is a bulky nucleophile. Bulky nucleophile. And this is secondary haloalkene. Also, if you see, beta carbon is crowded. And heat is also shown for our reasons. Thus, we can conclude that here elimination reaction is going to happen. This will be elimination in preference to substitution. And elimination occurs by what mechanism? Elimination occurs by E1 mechanism, because tertiary butyl alcohol is a weak base. Tertiary butyl alcohol is a weak base. It is neutral, right? Tertiary butoxide would be a strong base. Tertiary butyl alcohol will be a weak base due to neutral character. Okay, so E1 occurs because tertiary butyl alcohol is a weak base. Elimination occurs because of steric factors and heating. Steric factors are highly present in this reaction. It is already secondary, and we are using highly bulky base or nucleophile, and beta carbon is also crowded. So all these factors promote elimination, and elimination will be by E1 mechanism because tertiary butyl alcohol is the base, which is a weak base. So let's try to predict the product. Now we predicted the mechanism. Now let's look for the product. Okay. E1, right? First of all, carbocation has to form. This is a secondary carbocation. Carbocation may rearrange. You know, in mechanisms going through carbocation intermediates, there is always a possibility of rearrangements. We should not be avoiding that possibility. Rearrangements are the very nature of carbocations. So here, if we do a hydride shift, then we can get a tertiary carbocation, most stable carbocation. And then at the end, so this is E1 mechanism, we removed the leaving group first, we got the carbocation, then carbocation just did a rearrangement to make it more stable, and later the last step comes. Now the base is very weak base, that is why it waited till now, and now the base can take H plus from that carbon, and we will get a product like this. Remember, generally in E1 reactions, we are getting nearly always sets of product as the major product. In E2 reactions, if we use bulky bases, then there is a possibility of this Hofmann product dominance. Okay, this is E1 reaction. We will ultimately get more stable alkene. That is the states of alkene. Yes, and that is the final product, which is option 1. Okay, next question is, the major product obtained in the following reaction is, we are given with a secondary haloalkene, and we are using tertiary butoxide. If it is not clear, it is tertiary butoxide, which is a bulky, strong base and bulky base, right? Strong base, bulky base. Okay. and you know that secondary it is, and secondary the nucleophilic substitution is going to be difficult, and this will be primarily elimination reaction, and elimination reaction occurs. We have alpha, their beta is also present, and alpha beta, we have C6H5, then this product formation C6H5 at the end. Okay, so we get elimination reaction because of the steric factors present in this medium, right? Secondary it is, and it is a bulky nucleophile or base, and heating is also shown, therefore it is favoring elimination reaction. We get such a product, which is option 2. Next question, given with a haloalkene, this methyl group is not present, and NaOMe in methanol solvent. This is a reaction. Let me redraw it if there is less clarity for the image. They are showing sodium methoxide and MEOH. You should know that MEOH is a solvent and NaOMe is the main reagent. MEOH is just a polar protic solvent, and if we are taking sodium alkoxide, corresponding alcohol is often taken as the solvent. That is a general rule of thumb. If you are taking sodium methoxide, then you may see ethanol over here. If you are taking tertiary butoxide, then you may see tertiary butyl alcohol over here. So corresponding alcohol solvent is usually used in this reaction. And here let's assess what type of reaction it is. Okay, we know that SN reaction is the main reaction of haloalkene, and then there is a elimination reaction also, which is more dominant in this given settings. That is our question. So analyzing the structures, we find that this is secondary haloalkene, and this is the alpha carbon, and we can see beta carbon is highly crowded beta carbon. Okay, so already it is secondary and it is having a highly crowded beta carbon also, and this is a base, strong base as well. This is a good nucleophile and it is a strong base also. Therefore, it can show, depending on this structure, it can show either nucleophilic substitution or elimination reaction, and on this end there is a high steric hindrance present for nucleophilic attack. Therefore, elimination will be the preferred reaction. And if elimination is present, it will be by E2 mechanism, because MEO minus is the reagent. Alkoxide is strong base. Strong bases do E2 reaction. Okay, OMe minus is a strong base. It is showing E2 reaction. So we decided that this is elimination, not substitution, and then we decide that this is E2, not even. Just by looking at the solvent, you cannot say that it is even reaction. This is not even. Strong bases will not wait for loss of leaving group. Strong bases will directly attack on the beta carbon, beta hydrogen, and do an E2 reaction. Strong bases, that is why I said the role of solvent is secondary, but it should be present for promoting even reaction, if even reaction has to happen. Okay, here this is just E2 reaction because this is a strong base. Yes, if it is E2 reaction, then what would be the product? If it is E2 reaction, then this is the alpha carbon, this is a beta carbon, this is another beta carbon, and you can see that on this side no hydrogen is present, no beta hydrogen over here. But here we have beta hydrogen. Okay, here we have beta hydrogen. So only this can be taken by the base. There are no beta hydrogen, right? Okay, so OMe can take a hydrogen from this side because no hydrogen is present on that side. If there was one hydrogen, then that would be taken in preference and there an alkene would be formed. But here no hydrogen on that side and it has to occur by E2 reaction, then therefore H is taken from this side and such an alkene is formed by E2 reaction. Okay, no rearrangements. No rearrangement in these E2 reactions of haloalkenes. That is a final product. Okay, that is option 1. If it was occurring by, if such a reaction was occurring by E1 mechanism, then option 2 would be the answer. But here there is no possibility of E1 mechanism because base is highly strong. It will directly take H plus because no steric factors for taking H plus. Okay, no, there is nearly no steric factors for taking H plus, only that in certain cases, like if you use tertiary butoxide, tertiary pentoxide, in such cases the Hofmann product is dominating. In all other cases of E2 reaction and E1 reaction also, the more stable alkene is the major product, and if E2 reaction is happening, then it has to occur in single step. Therefore, if hydrogen is not present there, hydrogen will be taken from here and corresponding alkene will be formed. Okay, so that is the final product. The major product of the following reaction is, you can see a sequential reaction. First, they have given bromine. We know what is the role of bromine on this compound. This is doing an addition reaction, right? This is doing an addition reaction, right? Because here we can see an alkene. This is an aromatic ring that will not just simply react. This is an alkene, and alkene show addition reaction first. And then we are adding ethanol. Then we are adding ethanol. So let me redraw the structure. This is the question. So let's start. First of all, addition reaction occurs. We know cyclic bromonium forms from the previous session, and Br minus attacks on the carbon where positive is more stabilized. This is a benzylic position. This is a benzylic position, right? So there, positive is more stabilized. Therefore, nucleophile preferentially attack on that carbon. But doesn't matter if Br attacks there or here. But the products will be same. The product will be the same. A vicinal dibromide is obtained. Now we are adding ethanol. And if we are adding ethanol, what may happen? Now we have in hand an alkyl halide. This is an alkyl halide. And you know that alkyl halide react with small solvent molecules, small nucleophilic solvent molecules to give an addition, to give an SN reaction, right? This is solvolysis reaction. Methanol, H2O, ethanol, reaction with haloalkane directly is a SN reaction, solvolysis reaction, and we may think that here SN1 reaction operate because this is a secondary haloalkane first of all, and it is a benzylic haloalkane also. Which halogen will be displaced? This halogen will be displaced because this is more reactive, benzylic haloalkane, right? Benzylic halide. So, on adding ethanol, there is a carbocation formation first, that is SN1 mechanism, Br minus leaves, and then ethanol enters. This SN1 reaction, first leaving group leaves, then nucleophile attacks. So, we have listed that secondary haloalkane show SN1 reactions, tertiary show SN1 reaction, mainly primary show SN2 reaction, and if primary is beta crowded, then it can show SN1 reaction because the medium is polar protic, right? Polar protic solvent it is, and the carbocation is highly stable, then SN1 reaction can happen. Yes, that happens here. So first was an electrophilic addition reaction, and later we had a SN1 reaction. That way we can predict the reaction, and the final product will be this, not this, because this bromine was more reactive, and this will remain over there itself. Yes. The reaction happened without any heating because it was a benzylic halide. The second reaction happened without any heating because this was a benzylic halide. Otherwise, it is difficult to displace with such a weak nucleophile, right? Ethanol is a neutral molecule, weak nucleophile. Such weak nucleophiles cannot directly displace halogen in an SN reaction. We may at times require heating also to do that reaction. Okay? Yes. Anyway, here it was very easy. Being a benzylic halide that displaced, we get that product. major product of the following reaction is alcoholic AOH excess. Okay, alcoholic AOH is elimination reaction. We know OH minus in alcohol solvent is elimination reaction, and excess. Okay, we have two haloalkane in this. This is one, this is another, and you know that this is a strong base and it will be by E2 mechanism. OH minus, OR minus, their reaction will be by E2 mechanism, not E1. E1 is shown by weak bases only. And E2 reaction occurs. E2 reaction occurs to give more stable product, right? More stable product. If you think about this haloalkane, we have alpha here, beta there, beta here also. This beta has hydrogen, that beta also has hydrogen. Which one will be taken preferentially? This one will be taken preferentially because if you get an alkene over here, that will be more stable because it is in conjugation with the benzene ring, right? More stable alkene will be produced in elimination reactions. Let me redraw the structure, pH. So here OH minus takes this proton and leaving group leaves, that is E2, and on other side we have beta over there, beta hydrogen is present here also, and this will be taken preferentially because if this is taken, alkene is formed here and that will be again in conjugation with this new alkene, right? That will be highly conjugated alkene, then due to resonance that will be highly stable also, and therefore on that side OH minus takes this hydrogen in preference to that hydrogen to get the more stable alkene, and the product will be pH. Okay, here an alkene and then alkene, yes. So that will be the final product, and you can see that here you can see that this two pi bonds, they are in conjugation with the benzene ring like this. So this is highly stable alkene product, that is the major product, and this product is present in option. This is not that, option 3 only is the correct representation of that structure. You can see that in first case there is no conjugation, there is conjugation between these two only. This is not conjugated with this, and here this is conjugated with the ring, but that is not conjugated with this. They took the other beta hydrogen. Here this is not conjugated with the ring, so this is a different product. Here this is conjugated with the ring, this is also conjugated with this. So this is the correct product, correct final product of the reaction, and that is a more stable product. That is a more stable product. Yes. Here we have shown it in trans geometry also, right? This is a trans. The second alkene, this alkene part, there can be a confusion also. This should be shown in trans geometry. Trans is more stable, right? So that is more stable. The same thing is shown here also. This is shown as trans, just that is a different conformer of this structure. Both are identical structures, right? If you just rotate this structure about this CC single bond, you will get that structure, but that does not affect the trans geometry of this alkene. This alkene is trans here, trans there also. Both are same structures. Okay. Yes. So option 3 is the answer. Now next question. The major product of the following reaction is, we can see a tertiary haloalkane here. This is a tertiary haloalkane, and we can see a alkoxide here. Tertiary haloalkane with any alkoxide, you know, elimination reaction occurs, and since alkoxides are strong bases, it will be by E2 reaction. Okay, apply all the general principles, and if it is by E2 reaction and if it is ethoxide ion, we should be getting sets of product. If it was tertiary butoxide, then we may get Hofmann product, but if this is a ethoxide only, this is a very general case of E2, and we should get more stable alkene product at the end. Yes, so let's redraw the structure once again. Let me redraw it without using the wedge dash notations. C, Cl, CO, OET, and CH3, CH2, CH3. Okay, this is the structure given. This is alpha carbon, this is one beta carbon, this is a carbonyl. This is not affected here because we are using ethoxide only. We have here ethyl group, and this ethoxide will be replaced and keep on replaced with this same ethoxide ion present in the medium. So no change effectively happening at this center, although reaction would be happening frequently. Okay. Therefore, this is not our focus. We will be looking at the other beta carbon also. This is a beta carbon, that is another beta carbon. We are using small bases OET minus only. Therefore, sites of product has to be dominant. And if we are using tertiary butoxide, okay, without thinking about this portion, if we are using tertiary butoxide base, then this hydrogen would be taken away and here an alkene would be formed, Hofmann product. But here we are using ethoxide ion. Ethoxide is a small base. Small bases in general reactions will be giving us states of product, more stable product. So ethoxide ion from sodium ethoxide takes H plus from this carbon. Ethoxide ion from sodium ethoxide take hydrogen from this beta carbon, thereby does a need to elimination of halogen, and we get product as CH3, C double bond, CH, CH3, and here CO, O, C2H5. Right, that will be the product, sites of product. In the options they have shown a nucleophilic substitution here, a nucleophilic substitution here also. That does not occur. That does not occur because this is a tertiary haloalkane. We know the rule. Tertiary haloalkane with any alkoxides show elimination reactions, not a substitution reactions. So these are entirely wrong options. And if you look at the third and fourth options, here, this is the sites of product which we have drawn over there, and this is the Hofmann product which we are talking about, and this will be the major product. Okay, in general E2 reactions without using a bulky basis will be giving us sites of product only as the major product, more stable alkene as the major product. Okay, so this is the correct answer. Now a different question. CH3, CH, CH3, CH, Br, CH3 is just treated with methanol, CH3OH. So haloalkane treated with small nucleophilic solvent molecule, right? Then this will be SN reaction, nucleophilic substitution reaction, and this haloalkane is secondary haloalkane with beta carbon hindered also, right? Doesn't matter if it is a secondary haloalkane, it will be mainly by SN1 mechanism. No need to look at beta carbon. Yes, secondary haloalkane solvolysis reactions would be SN1 reactions, and this reaction therefore gives the major product as, let's check. First of all, leaving group leaves, right? SN1 means carbocation forms first, leaving group leaves, secondary carbocation forms, and then it rearranges because there is a possibility here this hydrate can shift from there to here and give rise to a more stable tertiary carbocation like this, CH3C, CH3 plus and CH2, CH3, that will be formed, and this is the most stable carbocation. It cannot be stabilized further. Tertiary most stable. Okay, so that was the initial steps of SN1. Now the nucleophile can attack, which is the solvent molecule, methanol molecule, CH3OH. Its oxygen is a nucleophilic center that attacks on this, and we get an ether, CH3, CH3, O, CH3, CH2, CH3. This ether will be obtained. That is a major product of this solvolysis reaction. Option 3 will be the right choice. Okay, next reaction, what will be the major product when metacresol is reacted with propergyl bromide? Okay, in presence of K2CO3 in acetone. Metacresol, we know from phenols chapter, this is metacresol. It is 3-methyl phenol. And it is treated with propargyl chloride. Propargyl chloride looks like this. Propargyl bromide they are taking. Propargyl bromide in presence of K2CO3 in acetone. Acetone is the solvent. Okay, what is the final product? You should know that this is Williamson ether synthesis. Okay, this is Williamson ether synthesis. You remember the reaction of alkoxides or aryl oxides or phenoxides. If it is SN2 that is giving ethers, such reactions are called Williamson synthesis reactions. Williamson ether synthesis. Once again, the reaction of haloalkenes with alkoxides or phenoxides, if the reaction is SN2, then this reaction is called Williamson synthesis. Once again, the SN2 reaction of alkoxides or phenoxides with haloalkenes producing ethers is called Williamson ether synthesis. Again, this is very relevant to our topic because these are SN reactions of haloalkene, right? We are talking about this only. Now, let's see what is happening here in the initial stage. Now, let's see what is happening here in the initial stage. You should know that K2CO3 is a base. This is a base. And you know why we are using base here, because this is acid. Phenol is acidic. Okay, so phenol is acid. If we are using a base, first phenoxide forms, right? CO3 minus, CO3 2 minus takes H plus, produce O minus over there. And this O minus is a nucleophile, then which is ARO minus, right? Then ARO minus attacks on the haloalkene, doing an SN2 reaction, because acetone is the solvent, SN2 reaction, giving us a ether product. That is the question. Now, let's quickly go back to the Williamson synthesis once again. First of all, we need to take alcohol. If we take alcohol, we can produce alkoxides in different ways. Either we can use sodium hydride base or sodium metal base we can use, or potassium metal base you can use. Such strong bases react with alcohol to produce alkoxides, which are substrates for Williamson synthesis. Which are the bases, which are the nucleophiles in Williamson synthesis. Okay, this RO minus attacks this, and for that reason it should be primary or secondary, right? It should be primary or secondary. It should not be tertiary, because we know if RO minus is reacting with a tertiary haloalkene, then it will give elimination reaction. Remember, increase in sterics favors elimination reaction, and that will give a alkene only then. That is not Williamson synthesis. Williamson synthesis is a SN2 reaction of alkoxides with suitable haloalkenes. Yes, so this happens and we get R, O, R dash as the product, which are ethers. And if you are taking phenols are more acidic, you know. Phenols pKa is 10. It is million times more acidic than most of the alcohols. So phenol, if we take, we can use weak bases as well for phenoxide formation. We can use NaOH, or we can use carbonate like potassium carbonate. These are weak bases. These are not very suitable there, but these are very suitable here because this is highly acidic hydrogen. Weak bases also can do this H plus removal of phenol, and here of course we can use sodium hydride or sodium metal they also will give corresponding phenoxide, but why to lose such strong bases for this simple reaction? So we will be usually taking, in the case of phenols, we will be usually taking either aqueous NaOH or aqueous K2CO3 for the reaction, for the phenoxide formation. Then this phenoxide, right? Then this phenoxide does an SN2 attack on the primary or secondary haloalkane, giving rise to ArOR dash, which is another ether. So these are Williamson synthesis. This is from alcohol phenol chapter, you know, and same is asked here. And let's outline the mechanism happening here. We are taking metacresol and we are applying K2CO3 in the mixture. Acid-base reaction occurs. Acid-base reaction occurs. Salt is formed. Salt is phenoxide O minus, K plus, and here CH3. Phenoxide is formed. Now phenoxide reacts with a primary haloalkane, which is propargyl bromide here. It is a primary haloalkane. Therefore, there occurs SN2 reaction. You know, primary haloalkane generally gives SN2 reactions, and SN2 reaction occurs like this. SN2 further, because acetone is the solvent, polar aprotic solvent. Anyway, final product will be like this, right? There is an ether now. There is an ether now. And we should identify that product from options. So from options, we can see that this is the correct ether product. These are not ethers at all, right? These are not ethers at all. So it is very direct. If you identify very fast that this is Williamson synthesis by looking at the base, by looking at the acid, by looking at the haloalkane, then you can easily solve this. Ether is the product. Okay, simply such groups will not be added on. Simply such groups will not be added on the ring, right? You know, ring substitution is little difficult, but these are very easy reactions that happens very fast. Okay, next question for the following reactions. We are given with a primary haloalkane, which is N-propyl bromide, and treated with a nucleophile. Nucleophile Z minus. Z minus could be ethoxide, or there they have shown tertiary butoxide. Ethoxide is called A. Ethoxide is called A, and tertiary butoxide is called B. Yes. So in place of Z minus, we can A or B. A is ethoxide, B is tertiary butoxide. Then we are comparing these two reactions. Okay. Here this is a primary haloalkane, and we are using a nucleophile as well as base. These are alkoxides. Alkoxides are strong nucleophiles, strong bases also. Therefore, both of them can show both nucleophilic substitution and elimination reactions on this primary substrate, right? They can do that. The question is that which is the major reaction, right? In both cases, you can easily predict that in both cases, major product will be SN reaction product, that are ethers, because both this is a primary haloalkane, and primary haloalkane sterics is very low, and primary haloalkane with alkoxides show SN2 reactions. Okay, now let's compare the two cases. If this is doing nucleophilic substitution, then we get an ether like this. And if Z is doing an elimination reaction with this primary haloalkane, then we get propene, right, like this. And the rate of substitution is, the rate constant for substitution reaction is given as Ks, the rate constant for elimination reaction is given as Ke. And you know rate constant from rate law, rate constant is just the rate of reaction when concentration of every substrate is unity, right. So Ks we can read as rate of reaction. This is rate only. If Ks is higher, rate is higher. That is the meaning. If rate is higher, K is higher. K is higher. Okay. Yes. Now let's try to compare. the question also. They are asking for this comparison, mu A versus mu B. Okay, mu A versus mu B, and they are defining mu as Ks by Ke. Mu is Ks by Ke. Okay, Ks by Ke. And they want the comparison between mu A and mu B. In which cases, if we use A, what is the mu value? If we use B, what is the mu value? Okay, we know that as Ks increases, mu increases, right? Or as Ke decreases, mu increases. Okay, this general idea we have from the expression. If numerator increases, mu increases. If denominator decreases, mu increases. Okay, this idea we know. And then just compare if we are using A, if we are using B, in which case Ks is higher or Ke is higher. Okay, imagine if we are using etho oxide, then there will be more Ks, right, than if we use tertiary butoxide, because tertiary butoxide is bulky. This is bulky base and bulky nucleophile. Steric factors increases, preference for elimination increases, right? That is the basic principle behind this. Remember the rules of substitution versus elimination. As steric factors increases, elimination increases, preference for elimination or the rate of elimination increases. So if we switch A to B, then more elimination happens, substitution decreases or elimination increases, right? Anyway, from moving from A to B, Ke increases, elimination increases, therefore mu decreases. Therefore, mu decreases, right? If we use A, the mu value will be slightly higher than if we use B, right? If we use A, Ks and Ke are there. If we use B, then now compared to previous case, mu value will be lower because substitution decreased, elimination increased on using B. Okay, so simply we can say that mu B will be less than mu A. Mu B will be less than mu A. Okay, apply the logics, apply the principles. You can easily say that mu B will be less than mu A, because if we use B, the elimination is increasing, substitution is decreasing due to steric factors, and therefore mu decreases. And so simply we can say that steric factors increases, mu decreases, right? As steric factors increases, mu decreases. Yes. Now they have to compare one more case, Ke versus Ke of B versus Ke of A. Okay, elimination rate constant for A and for B. Okay, this reaction, whether it is faster with A or B, that is a question. Okay, this reaction, elimination reaction, will be faster with B because there are more steric factors there. More steric means faster elimination. Okay, elimination is more preferred, right? So Ke will be higher if we use B in place of Z. Ke will be lower, elimination will be lower if we use ethoxide, because ethoxide generally shows more of substitution, right? So having that idea, this question was not about, okay, this should be very clear to you. This question is not at all about major product. They are just giving this pathway and that pathway, then they are just asking compare them together. This is not about major product. If they ask about major product, generally we should be saying this product is the major product in both cases. Okay, if we use tertiary butoxide, if we use ethoxide, in both cases, being it a primary haloalkane, we get nucleophilic substitution as the major product. Okay, but of course there will be competition with elimination. They are just asking about the competition with elimination. Okay, this question is not about major products. Yes, this pathway is going on in both cases, this pathway is going on in both cases. If we use A, both are occurring. If we use B, both are occurring, but there is some variation in both speeds of both reaction, right? That is the question. Yes, so Ke will be higher, elimination will be higher if we use tertiary butoxide. So we can say Ke with B is higher than Ke with A. Elimination will be higher with bulky bases, elimination will be lower. With small alkoxide, small alkoxides can do nucleophilic attack as well. Yes, so the option will be first one itself. Remember, tertiary butoxide is often called weak nucleophile also. Okay, tertiary butoxide is often called weak nucleophile due to steric factors. Weak nucleophile due to steric factors. Yes. Okay, next one. In the given reaction, 3-bromo 2,2-dimethyl-butane, ethanol. Major product A. Identify the major product. Okay, once again, 3-bromo 2,2-dimethyl-butane it is. Let me draw the structure. 2,2-dimethyl-butane. Okay, this is treated with ethanol, C2H5OH. What is the product? Oh, this is solvolysis reaction. Small nucleophilic solvent is that. Methanol, ethanol occurs. So the solvent is reacting with this. So that is SN reaction and SN1 reaction because it is a secondary haloalkane. And SN1 reaction and the final product will be ether. Final product will be ether, that we know. And what is that ether? That is a question. And first of all, Br has to leave. This is an SN1 we have fixed. And what is the first step? Carbocation formation. Then rearrangement occurs because it can become a tertiary if we do a methyl shift, right? So that is the new carbocation, tertiary, most stable carbocation. Now nucleophile can attack. Okay, SN1 it is, loss of leaving group happened, stabilization of carbocation occurred. Now nucleophile can attack. Nucleophile is our solvent itself, C2H5OH. Okay, C2H5OH attacks here. We get ether. Like this. Okay, this ether is the product. And they have given the IUPAC name as the options. So let's predict its name. 1, 2, 3, 4. So this is 2-ethoxy, 2,3-dimethyl, right? Butane. This is 2-ethoxy, 2,3-dimethyl butane. That is option 1. 2-ethoxy, 2,3-dimethyl butane. That is an SN1 product, rearranged product, right? Clear? So once again, this was the first rule for elimination versus substitution. The reaction of haloalkanes with small solvent molecules like H2O, methanol, ethanol, that is going to be SN reaction, that is generally called solvolysis reaction. And the mechanism here will be SN1 because it is a secondary haloalkane. Okay, next one. The major product of the following reaction, if it occurs by SN2 mechanism is, okay, this is very striking. This is Williamson synthesis. And you can see the base. We can see the acid over here. This is acidic hydrogen. Remember, acid-base reactions are very fast. Acid-base reactions are very fast than other type of reactions. So if there is a possibility of acid-base reaction, that will happen first. Okay, then only SN1, SN2, E2, such reaction will occur. So first of all, phenol is highly acidic and this is a base as well, and phenoxide forms. In presence of carbonate, it forms phenoxide. That is potassium phenoxide, then that is treated with this particular substrate. Haloalkane it is a primary haloalkane, it is an allylic primary haloalkane. That is why they have made a caution that if it is occurring by SN2 mechanism, okay, SN1 is also possible because it is an allylic halide, but they are saying you just do the SN2 reaction. Okay, so let's do SN2 reaction. SN2 is very easy. Do direct attack. on the alpha carbon, we will get ether, Williamson ether. Okay, that will be the final product, ether product. Yes, that is option 4. Yes, so alkoxides or phenoxides react with such primary or secondary haloalkanes, and that will be SN reaction in general, mainly SN reaction, and SN2 mechanism will be mainly happening. If we switch the haloalkane to tertiary, then there will be elimination reaction. Okay, that is our rule 2. In rule 2 we had mentioned tertiary haloalkanes plus any alkoxides will get elimination reaction. Okay, another haloalkane is given, NaOH, ethanol is given. So this is the reason for elimination. OH minus in alcohol solvent does elimination reaction. Since OH minus is a strong base, it is E2 mechanism. E2 mechanism means we have alpha here, this is a beta, that is another beta. So this beta is having a suitable hydrogen. So OH minus takes H plus from here and thereby cause elimination of Cl, and we get alkene product directly. E2 reaction it is, right? That is the product. That is option 4. Tertiary butyl chloride, then tertiary butoxide is taken, potassium tertiary butoxide. Major product they are asking for. We know in this place, be it any alkoxide, this is a tertiary haloalkane, right? Tertiary haloalkane with any alkoxide, we will get elimination reaction only, E2 mechanism. Okay, alkoxides, any alkoxide with tertiary haloalkane, CH3, let's highlight one beta carbon, all betas are equivalent. This alpha, these are betas, all betas are equivalent. Okay, and take an alkoxide here. This could be OET minus or OMe minus or OTBO minus. Be it any alkoxide, we get elimination as the reaction here. E2 mechanism happens because alkoxides are strong bases, and we get CH2 double bond, C, CH3, CH3. That is the alkene product of elimination. Right? So that again remembers about the rules. Alkoxides with tertiary haloalkane gives alkenes. That is simply due to steric reasons. Okay, steric reasons. Just keep in mind that this happened due to one more reason, that this is a strong base as well. Okay, this is a strong base as well. Alkoxides, everybody. This is not just occurring with tertiary butoxide. This is occurring even with methoxide being a strong base. All alkoxides show elimination reaction with tertiary haloalkane because of high basic character also of alkoxides. Yes. Okay, next question is, the major product of the following reaction is, this is also Williamson ether synthesis. First of all, we are taking orthocresol. Orthocresol is treated with aqueous NaOH, which is a base, right? OH minus is a base, this is an acid, so H plus is removed and we get corresponding phenoxide O minus Na plus. And then methyl iodide is given, methyl iodide, very easily SN2 reaction occurs. We get corresponding ether, right? Corresponding ether product, CH3 or CH3. So it is another case of Williamson ether synthesis. Williamson ether synthesis, remember, if SN2 has to occur, then it should be either methyl halide or primary halide, or sometimes secondary halide also. Secondary halide, you know, with alkoxides, secondary halides have high sterics also. If beta carbon is a little more crowded, then there is a possibility of elimination also. We have cited few examples previously. So remember about the basic principles always, and try to apply in every question. Okay, this is simple, direct, and product will be option 4. Okay, next question. We are given with haloalkane benzylic halides. They are benzylic halides, and let me redraw it, the structure. They have given structure of certain products also, their products also, like this. Okay, they have shown the products and they are asking for the mechanism. Okay, if this happened, what would be the mechanism behind it? So here, nucleophile, in first case, we know that this is benzylic halide. This is primary benzylic halide, classified primary benzylic halide. This is also primary benzylic halide. And benzylic halide has a tendency to do both the reactions, right? It can show SN2 reaction, it can show SN1 reaction as well. And here, what is the mechanism in either case? That is a question. So in the first case, if you see, the carbocation generated will be very stable, right? The carbocation generated over there, the primary benzylic carbocation generated over there will be highly stable. Just try to draw it. OCH3, CH2 plus, right? Remove the Cl. And this carbocation will be highly stable due to this plus R effect of OMe group. OMe is placed at para position, which highly stabilizes that primary benzylic carbocation. Already benzylic carbocation will be resonance stabilized. Other than that, it is more resonance stabilized due to OCH3 effect. Okay, so that OCH3 effect promotes SN1 reaction in first case. So first reaction should be SN1, right? It will be SN1 because of this high stability of this carbocation. Later only nucleophile adds, right? First carbocation forms, later nucleophile adds to get the product. But in the second case, that carbocation does not form, we can say, because that will be highly destabilized. That will be highly destabilized because of the strong minus R group. Strong minus R group. So CH2 plus E formed at all. You can see that this is strong minus R group. So that will create a positive charge on this carbon, right? And this positive and that positive will repel highly each other, and therefore this carbocation does not form, we can say. Okay, so the second reaction occurs by SN2 reaction mainly. Okay, it is entirely, we can say it is entirely occurring by SN2 reaction, that is entirely occurring by SN1 reaction due to the high stability of that carbocation, that is due to very low stability of this carbocation. Okay, so benzylic substrate, we know there is a possibility of both SN1 and SN2, and this case we can decide simply by looking at the corresponding carbocation stability. Yes, so there should be a direct attack happening on this to give that product. Yes, so we decoded the mechanism, SN1, SN2 in second case, and then the options, reaction 1 is of second order, no, SN1 is first order reaction, SN2 is second order reaction according to its right advanced step, right? SN1 is first order, reaction 2 is second order. That is the correct answer. Okay. So next question, 2-methyl propyl bromide. 2-methyl propyl bromide reacts with ethoxide gives A, reacts with ethanol gives B. What is the mechanism and products in both cases? Okay, so that is the final question for us. 2-methyl propyl bromide. Let's draw it. 2-methyl propyl bromide reacts with ethoxide and same thing reacts with ethanol. What is the product? Okay, in the first case we have a primary haloalkane, right? Primary haloalkane, then there should be a SN2 reaction because this is a strong nucleophile. Okay, primary haloalkane, there should be SN2 reaction, nucleophilic substitution reaction first of all. Okay, first of all we should know that these are both SN reaction, not elimination. Okay, that is the first factor. We know that there is a competition between SN and E reactions, and first of all we have to decode them, whether it is SN or E. So we are clear that both are primary haloalkane, therefore it will be more like SN reaction, right? And in SN reaction, what would be the mechanism, that we should think later. Okay, SN reaction with strong nucleophilities, that is SN2, therefore SN reaction with weak nucleophile, ethanol, and primary has a hindered beta carbon also. So this solvolysis reaction, second is a solvolysis reaction, that will be SN1, right? Tertiary haloalkane with small nucleophilic solvents, SN1, secondary also SN1, primary generally SN2, and primary with hindered beta carbon SN1. So using that logic, we can say that primary ethanol reaction, small solvent molecule reaction, SN1. Okay, so in the first case, we'll get an ether like this. There is a Williamson ether synthesis. Okay, remember the alkoxide reacts with alkyl halide in SN2 fashion, that is called Williamson synthesis. Okay, we get that ether. And in second case, solvolysis reaction, SN1 mechanism, we have predicted it, and first primary cation forms, then it rearranges to a tertiary very quickly because we have a hydrogen which undergoes shift to that side, and we get tertiary butyl carbocation on which ethanol molecule attacks. To give corresponding ether again. Right, solvolysis using alcohol solvent also produces ethers. Using aqueous, using water produces alcohols. Right. Yes, so these are the products, and both are ethers, but different ethers. Now let's identify the options. First reaction is SN2. Mechanism followed in the first reaction is SN2. And first compound is, this is isobutyl ethyl ether, right? Isobutyl ethyl ether, that is true. This is 2-butyl ethyl ether. No, it could be secondary butyl. Anyway, that is wrong. And second mechanism, second reaction, we are having SN1 reaction, that is solvolysis of primary with crowded beta, that will be SN1 reaction, and SN1 correct, and that is, the product is, yes, tertiary butyl group and ethyl group, tertiary butyl ethyl ether, tertiary butyl ethyl ether. Yes, option 1 will be the correct choice. So these are the few questions which are closely related to our discussion, and such concepts have been used in multiple places also, and this topic which is nucleophilic substitution versus elimination is not only for haloalkanes. This competition is there for alcohols, ethers also, and since this is very detailed and this is not very simple, you may understand this is not very simple. We have to use our logics, we have to look at their logics, the compounds logics also. So this is little complicated, and this is complicated because there is a lot of nucleophile options. It could be H2O, it could be OH minus, it could be alkoxide, it could be tertiary butoxide, it could be tertiary butyl alcohol. In every case there is a different behavior may happen, so we have to analyze it, right? Every time we have to analyze it, keeping the basics are very simple. There are only 3 or 4 points there to remember, and using that we have to decide what is mainly happening in the given conditions. Okay, so this competition will be there for alcohols also, which we will deal later in today's session. In this second session of our organic summary series, we had discussed about nucleophilic substitution SN1 or SN2 versus elimination E1 or E2 of haloalkane substrates. Remember, these two reactions are the most favorable reaction or most common reactions of haloalkane substrate. These are not very common on alcohols or ethers for some reason, which there is no leaving group present in alcohol or ether directly. Okay, here in haloalkanes, they are already leaving groups. We don't have to modify it to be a leaving group, right? Therefore, it is directly occurring. The elimination and substitutions SN1, SN2, E1, E2 are directly occurring on haloalkanes, but it is not very direct on alcohols and ethers. We have to create a leaving group first in them, then only these mechanisms can operate there. Okay, that is a difference. So we will discuss them later in a later session. So hope you understood the basics and the connections. Okay, more than basics, it's connections between the different aspects. Here we have discussed about a variety of reactions we have prepared. If you think about the topic once again, we had prepared several alcohols, several ethers by different mechanisms, different alkenes by different mechanisms. Okay, so that was the purpose of this session. Okay, once again, while solving such problems, you try to recollect all the informations, all the basic principles involved in it. That way we can easily score in this particular type of questions. Okay, thank you all the best.